In this video, we are going to be learning about the developments that led to Bohr's atomic model. And we're specifically going to be talking about the wave nature of light and electromagnetic radiation. So, interaction of radiation and matter, they have given a lot of information about the structure of atoms and molecules. In fact, you have a separate um, study, or rather a separate branch called as spectroscopy, which deals with the interaction of atoms and molecules with electromagnetic radiation. So there are certain properties that were not explained by Rutherford's atomic theory. So those were the stability and the arrangement of electrons. Those are the two main drawbacks. But apart from these two, there were two new concepts that could not be explained by Rutherford's atomic theory. So the first is the dual character of electromagnetic radiation, and the second is atomic spectra. So we'll be learning in detail about these two. So let's start. First of all, wave nature of light and electromagnetic radiation. So in the 19th century, physicists studied the absorption and the emission of radiation by heated objects, and this is called as thermal radiation. Where they, so it's known that thermal radiation is made of electromagnetic radiation of various frequencies. It was Newton who said that light is made up of small particles called as corpuscles, which explain the concept of reflection and refraction. I'm sure you would have learned. Reflection is basically a light ray hitting a particular um, object and then it reflecting back. Basic idea of a mirror. Refraction is the whole having your pencil inside a transparent glass of water. You can see there is a slight difference because when light goes from one medium to another, it leads to a certain change in its speed. Or rather, sorry, not speed changes, along with it, the angle also changes. But this particular concept of light being made of small particles did not explain the concept of interference and diffraction. So, diffraction is the bending of waves around an obstacle. So, like you have a simple example could be if there is a light switched on inside a room, and then in the adjacent room it's off, and you open the door, you can see that. There is not a particular straight line, but there is a gradual fading of light. I mean, in simple terms. Okay. So it could not explain diffraction and interference. Interference is a combination of two waves of the same frequencies or different frequencies, and they gave wave whose distribution at each point in space is the algebraic or vector sum of disturbances at that point resulting from each interfering wave. I'm hoping you learned this in physics, but in essence, the particular nature of light did not explain the concept of interference and diffraction. It was Huygens who proposed the of wave-like character of light, and this in turn explained the two concepts, that is diffraction and interference. So one more important person that we need to remember is that, oh, never mind. We will talk about him when we talk about electromagnetic radiation. Anyways, so wave motion. So wave motion is this disturbance that originates when there is a vibrating source. Okay, and so this leads to the formation of this alternate crests and troughs. So crest is the top part. I mean, A is the crest and is the maximum upward displacement, and trough is the point of maximum downward displacement. This is an example of a wave motion, and this is the direction, right? So so there are certain terms that you need to know when we talk about a wave. First is a wavelength. So wavelength is the distance between two consecutive or adjacent crests or troughs. So this is the wavelength. This is also wavelength, and it's denoted as lambda, and since it's basically the distance, its units is meter or angstrom. Frequency is the number of waves that pass through a point at a particular in a second. So its unit is second inverse, and it's also hertz. So the number of waves that pass through a given point in 1 second. Velocity is the distance traveled by waves in 1 second, whereas amplitude is the height or of the crest or the trough. So this height of the crest or the trough is the amplitude, whereas wave number, that is mu bar, is the number of waves per centimeter. So c, that is the velocity, is equal to the frequency into the wavelength. So velocity equal to mu into lambda. Mu is equal to c by lambda, and 1 by lambda is equal to the wave number. So wavelength 1 divided by the wavelength gives us the wave number, which is denoted as mu bar. So from the so since c into 1 by lambda equals to mu, this implies that mu equals to the velocity into the wave number. So these are some of the important terms that you need to know when you learn about waves. Ah, So electromagnetic radiation. So it was actually James Maxwell who proposed that light. If you remember, we'd also studied about Maxwell's electromagnetic theory of radiation. If you don't remember, to check out the Rutherford's model of the atom. Anyways, James Maxwell proposed light and forms of radiation, they propagate through space in form of waves. So he said that these lights move through the form of waves, and these waves have both electrical as well as magnetic field, and these radiations are called as electromagnetic radiations. So they consist of an electric and magnetic field which are perpendicular to each other. In this image, or yeah, this animation, I think. Anyways, you can see that the electric and magnetic field are perpendicular to each other, and these both are also going to be perpendicular to the direction of the propagation of the wave. So they both have the same wavelength as well as frequency, and the electromagnetic waves travel at the same speed of light. So that's 3.00 into 10 to the power 8 meters per second. And unlike sound, they can travel through vacuum. So they do not require any medium for propagation. If this was not the case, we would not be receiving the light or the radiation from the sun. So characteristics, three main characteristics, consist of an electric and a magnetic field, which are perpendicular to each other. They are also perpendicular to the propagation of the wave. They have the same frequency as well as the wavelength. Electromagnetic waves travel at the speed of light, that is 3 into 10 to the power 8 meters per second. And unlike sound, these can travel through vacuum. So from that, we get the electromagnetic spectrum. So electromagnetic spectrum is basically the arrangement of different types of electromagnetic radiation in the increasing order of their wavelength or decreasing order of the frequency. So these are various types of rays that you observe, and we technically can't be seeing all of this. We can only see this teeny tiny portion in between. That is the visible spectrum. As your Vibgyor, the your rainbow, yeah, all the colors that you can see comes under the visible spectrum. The others are not visible to us, but they are quite useful in our day-to-day lives. Think about it. So you have radio frequency. It's around 10 to the power 6 hertz, and it's used for broadcasting. Your FM, AM, all of these are radio frequencies. Microwave region, the whole heating, the whole microwave industry is dependent on this, and it's around 10 to the power 10 hertz, and it's used for radar and microwaves. Infrared region, 10 to the power 13 hertz, used for heating. This one, IR. The small portion at around 10 to the power 15 hertz is the visible light, and it only this can be basically seen with our eyes. We require special instruments to detect the other types of radiation. And ultraviolet region is 10 to the power 16 hertz, and it's an important component of sun's radiation, and that's why we keep saying that we need to be cautious about UV rays, right? That's why we use sunscreens. The X-rays are 10 to the power 18 hertz. That's the the whole, you can see the skeletal system with the help of X-rays, if you remember. Gamma rays, if you, I think we've also learned about gamma rays when we studied about the various radioactive decays. So it is more than 10 to the power 19 hertz. So these are the various ranges in the electromagnetic spectrum. Whatever I read right now were in hertz, which means we're not talking about wavelength over there, we were talking about the frequencies. So in this video, we studied about the properties of waves. We studied about the fact that it was Newton who suggested that light is made up of particles, whereas Huygens suggested the light might be made of waves. So based on these two, the particle nature of light did not explain the concept of diffraction and interference, whereas the wave nature was able to explain these two. And we studied about the characteristics of electromagnetic radiation, the electromagnetic spectrum. In the next video, we are going to be studying about black body. Oh, sorry, we are going to be studying about the particle nature of light, specifically about black body radiation.